Okay, so we're going to talk about rational functions today and Friday. I'm giving you a take-home quiz today. Don't leave class without getting one. I'll hand it out towards the end of class. So if you leave early, you got to make sure you ask me for one. Okay. And then, so that quiz will be due next class on Friday, and then on Wednesday of next week, project 3 will be due. Okay, so let's go through the preview exercises together. So I have a graph of a function here, and I just have a few questions about it. So are there any values of x where this function is undefined, that are not part of its domain? Yes. When x is 1, right, there's an asymptote there. So my graph actually gets infinitely close to 1 from the right and infinitely close to 1 from the left, but never actually touches or crosses that line. X equals 1 is not, the function's not defined there. Anywhere else? 2, yeah. There's a hole in the graph right there at x equals 2. Yeah, so there are 2 x values where this function is not defined, meaning there's no y value there. So at x equals 1, there's no y value for the function. At x equals 2, there's no y value for the function because there's a hole. All right, so what's the equation of the vertical asymptote? How do you write the equation for a vertical line at 1? Yeah, x equals 1. Every point on that line has an x coordinate of 1. It's 1, 0, 1, 1, 1, 2, 1, 3. So every point on that line has an x coordinate of 1, so that's its equation, x equals 1. And then there's also a horizontal asymptote in this graph. Y equals 0. The x-axis, yeah, is a horizontal line that the graph approaches from above and approaches from below, never touches, never crosses. That is the line y equals 0. Okay, so the function we just studied is an example of what's called a rational function. And a rational function is a ratio of 2 polynomial functions. So we just spent 4 days, I think, talking about polynomial functions. So a rational function is just a fraction where you have a polynomial on the top and on the bottom. And the bottom cannot be 0. That's all. So here's an example. We've got x squared plus 5x plus 8 over x times x minus 4 times x plus 2. It's a polynomial on top, and that's a polynomial written in factored form, but still a polynomial on the bottom. So the domain of a rational function is a set of all numbers except any x values that will make your denominator 0. Right? So that's the only thing I have to be careful about when I have fractions, is making a denominator 0. So what values of x would make this denominator 0? 0, 4, negative 2. So if I was going to write this as a domain, right, my domain would be the set of all x's such that x is not 0, 4, or negative 2. So that's how I would write it with set builder notation. Interval notation is going to be a little bit more cumbersome, right? What's the smallest excluded x value here? Negative 2. So I could write this as negative infinity to negative 2. Make sure you don't include that negative 2 by using a round bracket and not a square bracket. So all the real numbers, all the way to negative infinity, up to negative 2, but not including negative 2. Then union that with, I'm going to start at negative 2. Again, I'm not including it, so by using a round bracket on both, I'm saying you jump over that 1 point, negative 2. My next smallest x value is 0 that's excluded, so I put 0. Don't include it because it's not part of the domain. Union that with 0 to 4, not including the 4, and then union that with 4 to infinity. Okay, so I want to investigate what happens near a value that's excluded from the domain. So we know how to find what values are excluded. Want to think about what happens near those values. So I'm going to start with the simplest rational function, which is f of x equals 1 over x. What value is excluded? What value of x can you not plug into that function? 0. Good. So I'm going to investigate what happens to the function 1 over x when x gets closer to the excluded value of 0. So in this table, I'm going to have x values approaching 0 from the right. So picture 0 on a number line. And I'm going to put in things that get closer and closer to 0, starting from 1 on the right of 0. So I'm going to put in a 1, then a 1/2, then a 0.1, and get closer and closer and closer. Okay. So what happens if I put a 1 into 1 over x? You get a 1. Yeah. What happens if I put 1/2 in? What is 1 over 1/2? 2. Good. Yeah. What's 1 over 0.1? 10. 1 over 0.01? 100. 1 over 0.001? 1000. Okay, so what does it look like is happening to the function values as x gets closer to 0? They're getting bigger. So we could say they are approaching infinity. Okay. So as the x values approach 0 from the right, the values of f of x, or the y values, approach infinity. Okay, so the shorthand notation for that sentence that I just read in English is right here. This says as x approaches 0, and that little plus means from the right. As x approaches 0 from the right, f of x approaches infinity. Okay, I'm going to do the same thing, but this time I'm going to approach 0 from the left. So if you picture a number line, here's 0. I'm going to start at -1 and get closer and closer to 0 from the left side of 0. So what do you get if you plug a -1 into 1 over x? -1. 1 over -1 is -1. What if I plug in -1/2? -2. -0.1 will give me -10. -0.01 is -100. And -0.001 is -1000. So as the x values approach 0 from the left, the values of f of x approach -infinity. Good. And again, that's how I would write this in a shorthand notation. As x approaches 0, that little upper negative sign means from the left, f of x approaches -infinity. So in this case, what we have is a vertical asymptote. My graph, when I approach from the right, goes up, shoots up. And when I approach from the left, shoots down, right? So it goes whoosh, and you end up with an asymptote at x equals 0. So we know what happens near x equals 0. Let's investigate some other characteristics of the graph. Does 1 over x have any x or y intercepts? No, right? If I want to find x-intercepts, we typically make y 0 and solve for x. But the only way a fraction can ever be 0 is if its numerator is 0, right? Yeah, and in this case, my numerator is 1, right? No matter what I put in for x, 1 divided by something will never equal 0. Okay, so this has no solutions. All right, and then to find y-intercepts, you typically make x 0. So I would plug in 0 for x, I get 1 over 0. And what's that? Undefined, yeah. So there are no x or y intercepts for this graph. And then I want to think about the end behavior. Think about what happens as we go really far to the right. So let's say if I say as x approaches infinity, f of x approaches, what happens to 1 over x when you put bigger and bigger numbers in for x into that denominator? It gets smaller and smaller, like you get 1 over 10, 1 over 100, 1 over 1,000. So f of x is going to 0. And then let's see what happens as x approaches negative infinity. F of x approaches. So I'm going to put in negative 10, negative 100, negative 1,000. What am I approaching for the other one? You're still getting closer to 0. Yeah. They're just it's just through the negative numbers, right? So here we were getting closer to 0 because we were doing a tenth, a hundredth, a thousandth, a 10,000th, right? Closer and closer to 0 from the right. Now we're getting closer and closer to 0 just from the other side of 0. So it's still approaching 0. So my end behavior at both ends is my graph is approaching 0. So in this case, we have a horizontal asymptote. The line y equals 0 makes a horizontal asymptote based on this end behavior. So I'm going to try to sketch a graph of 1 over x based on the things I've discovered. I know I have a vertical asymptote at x equals 0. So I typically draw vertical asymptotes in as dashed lines because they're not actually part of the graph. They are just guidelines for how to draw the graph. So I make them dashed. So I have a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. So I put those in. I know that my end behavior to both ends is 0, right? And it might be helpful. We did recognize that in this first case, it was approaching 0 through positive values. And in this case, we were approaching 0, but through negative values. And I know from those tables that I did, as x gets really small, as my x values get close to 0, my y values blow up. So as my x values get really close to 0, my y values are going to blow up. So I've got something like this. And then my end behavior, I approach the asymptote. My end behavior approaches 0. And then according to the second table, where I was approaching 0 from the left, when x gets really close to 0 from the left, y goes to negative infinity. Okay, so when I get really close to an x equals 0, my y values get really small, so I've got something like this. And then my end behavior says I'm going to approach 0, which is my horizontal asymptote, through negative values, so below the x-axis, through negative y values. So that's a graph that looks like the graph of 1 over x. So this is a new parent function to add to your list. Okay, perfect, yeah. So before I look at another new parent function, I'm just going to jump to the class activities and do number 1 with you. So I have this new parent function, 1 over x. How would I graph 1 over x minus 5? What kind of transformation has taken place? I moved it 5 to the right, yeah. So I could say that I could just write myself a little note. This is 1 over x shifted 5 to the right. Okay. So that means that my vertical asymptote that used to be at 0, now it's going to be at 5. Everything else stays the same. Shape and everything looks exactly the same. So it looks something like this. It's your basic. Like that. So you get the basic shape, and then you just figure out where the asymptotes go, and we just shifted the whole thing. So I'll leave you to answer all these other questions. The parent function was 1 over x, and we just shifted it. Okay, so let's go back to study another new parent function. Another new parent function, this is another rational function, it's 1 over x squared. What value is excluded from 1 over x squared? No, I can square negative numbers. 0, I can't put 0 in a denominator, so 0 is excluded again. So let's think about what happens when x gets near the excluded value, right? X is excluded here. So I want to think about what happens as x approaches 0 from the right. Okay, so think of 1 over x squared. If you plug in smaller and smaller values for x, what happens to 1 over x squared? It's larger. Right? If you put in a tiny number into a denominator, like 1 divided by 1, 1 divided by a half, 1 divided by 0.1, so your denominator is getting tiny, which means you're dividing it into 1. It's going to go in more and more times. So this is going to approach infinity. Let's see, what happens as x approaches 0 from the left? So now we're plugging in tiny, tiny numbers for x, tiny, tiny negative numbers like negative 0.1, negative 0.01. But what happens when you square a negative number? It becomes positive, yeah. So I'm going to have 1 divided by a really tiny positive number. It's still going to approach positive infinity. So this is a little different from 1 over x. 1 over x was it went to positive infinity at the right and negative infinity at the left. This one, they both go up. All right, let's look at the end behavior. What happens as x gets really big as opposed to really small, which was what I did last time? If you plug a big number into the denominator of 1 over something really big is really small, right? So f of x is going to approach 0. And as x approaches negative infinity, f of x approaches what? 0 again, yeah. So now I'm plugging in really big negative numbers, but when I square them, they become even bigger positive numbers. So negative times negative is positive. So it's going to approach 0, and it's through positive values. So both of them approach 0 through positive values. So what's the equation of my horizontal asymptote going to be? Close. Y equals 0. X equals 0 is my vertical asymptote. Yeah. This is my vertical asymptote, VA for short. This is my horizontal asymptote, HA for short. Does 1 over x squared have any x or y intercepts? No, you can't plug 0 in for x, so there's no y intercept. Yeah, 1 over x squared can never equal 0. The only way a fraction can equal 0 is if its numerator is 0, and this numerator is always 1. No way to make it 0. So this is nope. Okay, so I want to graph it. It might be helpful if we know if it has any kind of symmetry, right? So we will answer that after we draw it. Okay, so I've got a vertical asymptote at x equals 0, horizontal asymptote at y equals 0, and I know my end behavior at both ends approaches 0 through positive values. And I know that when x gets really close to 0, when I get really close to 0 for x, my y values get really big. So this is going to do something like this. And then these come down towards 0. Yeah. Does it look like, what kind of symmetry is that? Y-axis symmetry, also known as an even function. Right, so this is y-axis / even. And then to confirm that algebraically, we want to plug in a positive x. 1 over x squared, and then a negative x, 1 over negative x squared. And then see if we get the same thing. The y-axis symmetry, they should be the same thing. So negative x, when you square it, what do you get? Positive x. So this is the same thing as 1 over x squared. So these two are the same. And when f of x equals f of negative x, that confirms that we have y-axis symmetry. All right. Before I send you on to the activities, I want to just quickly go back to 1 over x. Right here. What kind of symmetry does that graph have? Origin symmetry. Origin, or also known as odd. Yeah. Okay, so to confirm that algebraically, I have to evaluate f of negative x and negative f of x, right? So opposite x values are supposed to give you opposite y values to get odd symmetry. These should be the same to have an odd function. So if I plug a negative x in, I get 1 over negative x. If I put a negative in front of f of x, I get negative 1 over x. Are those the same? Yeah, how come? Yeah. When you're dealing with a fraction that has a negative, you can put that negative in the numerator or the denominator or out front. All means the same thing. Because in this first example, this is 1 divided by a negative number. A positive divided by a negative is a negative 1 over x. Okay. So these are the same, and that confirms that I have origin symmetry. Okay. When f of negative x is the negative of f of x. All right, so let's look at, you're gonna come back to number 1 and finish it in a minute. Let's look at number 2. I have 1 over x minus 2 squared minus 4. Because I have a squared in the denominator, my parent function is going to be 1 over x squared. And then what transformation has happened? Two to the right and down 4. Shift to right, down 4. So that means I can just draw it right now without answering all these questions. I'm going to leave the questions for you to do when you come back. But if I draw it, my asymptotes used to be the axes. I have to shift them to right and down 4. So this one goes to the right. My x-axis has to go down 4. So now everything's shifted and I can just draw the same shape because there's no shape change. So this just goes like this. And same thing on the other side. All right, so now I've just sort of given you a little head start in the activities. I'm going to let you go back and answer the questions and do the rest of them.